So if we have a generic problem, generic, okay? Z is, we have this function of x and y, right, plus lambda and our constraint, which is also a function g of x and y. Okay? Yes? We take this and we're going to get f of x equals 0. We're going to get f of y equals 0, or z of x and z of y, right? And we're going to get z of lambda. Yeah, that's a lambda. Isn't that perfectly looks like a lambda? Z of lambda equals 0. Now those are the first order conditions that our three partial derivatives are equal to lambda, are equal to 0, including lambda now. Okay? So we have more exciting first order conditions. Now, what are the second order conditions? Well, we were building this Hessian, right? That was xx, xy, yes, yx, and yy. Okay? Now, we're going to take this and we're not going to put the lambdas out further. We're going to put the lambdas around. All right? The B in the budget, like that, 12, right? The 12. That's a constant. What's its partial? What's partial is a 0. So we're going to put a 0 here. Okay? And then we're going to put the coefficients from here. Okay? And the coefficient there is a 1, and the coefficient there is a 1. So we're going to put 1, 1, 1, 1. And we're going to put a little h here for Hessian, but we're going to put a bar over the top of it, and we're going to make it look like that. And that's called a bordered Hessian. And you're like, seriously, it's the end. Yes, that's why we saved the fun stuff for last. It's a bordered Hessian. A bordered Hessian. A bordered Hessian. Now, we already know what the answers to this are, more or less. Because that's minus 6, that's 0, and that's minus 12, right? This thing down here, this last part, that's the second order conditions from unconstrained, right? When we did this without a constraint, that's that. Now we're doing it with the constraint. Okay? We're doing it with the constraint. With the constraint. Okay? Are we excited by that? Yeah, we're doing it with the constraint. Okay? No? No, no, no. Okay. Now, in one sense, this is way easier now. So let's rewrite this. Here's my bordered Hessian. H1 is 0, and it's always 0, right? It's that part. So that's worthless. I don't need to even calculate that. H2 is going to be 0 times something minus something squared. Something else squared. All right, so this is always going to be 0. And these two are always the same number, right? This is you know, zx lambda, and this is zx, z lambda x. They're always the same. This is always symmetric. So H2 is always going to be negative because it's going to be 0 minus a positive. Okay? This is always going to be 0 minus a positive number. And it's always going to be negative. So who cares? We're not calculating that one either. So the only thing we need to calculate in this is the determinant of the whole thing. Yes? And so we have 0 times minus 6, 12, 0, 0. Minus 1 times 1 minus 6, 1, 0. Plus 1 times, yep, I screwed that up. 1, 1, 0, 12. Plus 1 times 1 minus 6, 1, 0. Okay? So that's 0 minus 12, yes, plus 6 is minus 6. Okay? It's less than 0. If it's negative, this is a minimum. Okay? Now, funny, the fact that this negative means it's positive definite. The matrix is positive definite. Okay? And I know that screws with your mind. The negative is positive definite. But this is a minimum. It's a negative number. It's a minimum. Okay? We haven't maximized the function. We know that the maximum of the function is all the way up at the top. This is one of those functions that goes like this, right? And that's 150 up here. Okay? So we found a point which is a minimum. It's a minimum. A minimum. No? It's a minimum. Now, what's lambda? Right? So x and y are 4 and 8. What's lambda? The minus 12y equals lambda. Y is 4, so lambda equals minus 48. So if I were to change this constraint and make it 13, if I were to change this constraint and make it 13, if I were to change this constraint and make it 13, or make it 11 rather, change it by 1, 11 or 13, either way. I make it 11 or 13, I would expect it to change by, okay? So if I make this, so when the constraint is 12, lambda is minus 48. And z is was minus 100 and something, right? No? Yeah. It's minus 138. Okay? If I make the constraint 11, z should be somewhere around minus 90. It will change. If I make the constraint 13, z should be somewhere, and that's what that squiggly thing means, somewhere around minus 188. Or 186, sorry, 186. Okay, around there. It won't be exactly there because lambda is really for minuscule changes, not from going to 12 to 13, but from going to 12 to 0.0012. From going to 12, instead of 12, we go to this, then maybe lambda will be fairly accurate. Going from 12 to 13, lambda's not going to be that accurate, but it'll get us in the ballpark. And in fact, if we go to 11, if we redo this math with 11, and here's a good project for you because you're bored and you have nothing else to do. If you want to experiment, you could do this, and you'll find out that in reality it works out to be minus 92, which isn't bad. It's not great. Is not great, but isn't bad. Okay? No? It's beautiful. Okay. Do we want to do another one? Do another one? Yeah? Yeah? Do another one? Okay. Is that beautiful? Yeah, you're like, yeah, 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 yeah. So zx equals 16x minus y equals 0. Zy equals minus x plus 24y. See, you made me screw that up already. Made me screw that up already, and I'm blaming you guys. 8x squared minus xy plus 12y squared plus lambda times 42 minus x minus y. That's our Lagrangian, right? So there's a minus lambda on here equals 0, minus lambda equals 0, and then I do z lambda, which is 42 minus x minus y equals 0. Okay? Now you're like, really, I don't want to solve that. And I'm like, yes, you do, because it's not hard to solve. No? No? Yeah, it's not hard to solve. So x equals 25, y equals 17. Those two add up to 42. Lambda equals 383. And that's my solution. So we have 25 and 17 is the answer to this equation. Okay? If I change the 42 to 43, I will gain 383. If I put 25 in here, so I go 8 times 25 squared minus 25 times 17 plus 12 times 17 squared, that's what z is. If I change this to 43, this will get bigger, that'll get bigger, and the value of the equation will get bigger by 383. Okay? If this is, C will go up by about 383. Now, he said, now, what's the bordered Hessian look like? Well, I got a 16 there. I got a 24 there, right? So zxx equals 16. ZYY equals 24. And Z lambda lambda, as always, equals 0. And the coefficient here is 1, and the coefficient there is 1. So my bordered Hessian is going to be 0, 1, 1, 1, 1, just like before. 16, 24. Oop. But now, ZXY is minus 1, which means ZYX equals minus 1. ZX minus, so they're both minus 1s. So I have a minus 1 there and a minus 1 there. Okay? If I'm sliding through some of these partials, go back and look, right? This is your job now. You should have an just automatic, I'm solving the partials thing going in your head. Yes? Because that's what we does. Well, I don't need to calculate H1 and I don't need to calculate H2, right? H1 is 0. H2 is minus 1. I know what they are. This is 0 and that's negative. And I know that that's what they're going to be. The only thing I have to calculate, okay, is the H3. Yes? Okay. So that's 0 times 16, 24, minus 1 and 1, plus 1 times 1, 1, minus 1, 24, right? Minus 1, that's minus, this is plus. 1, minus 1, 16, 1, minus 1. So that's 0 minus 1 times 24 plus 1 plus 1 times 1 minus 16, right, is 0. Minus 25 minus 16 is minus 41. Yeah? Minus 41? Minus? That's less than 0. This is a minimum. It's positive, definite. Definite. Yay, us. Us is so good at this. Isn't us? Us is. Us is so good. Good we are. Are we good? We are good. Let's do one more generic one for no good reason. Yeah? Yeah? Okay. So, which isn't a whole lot different than one we've already done. Okay? But I can remind you of something else. So what I'm doing is maximizing 2x squared plus y squared plus lambda 12 minus x minus y. Okay? Right? So f of x is for x minus lambda equals 0. F of y is 2y minus lambda equals 0. And f lambda is 12 minus x minus y equals 0. Okay? And again, if I solve that, I'm going to get x equals 4 and y equals 8. Yeah? And if you're saying how to do that, well, the easiest answer to that is Cramer's rule, but we'll do that again in a second. Okay? No? Yeah. And so we get 0, 1, 1, 1, 1, right? 4, 2, 0, 0. That's our bordered Hessian. We don't need to do H1 or H2. They're boring, right? So we just do the whole thing, which is 0 times 4, 0, 0, 2, minus 1 times 1, 1, 0, 2, plus 1 times 1, 1, 4, 0, equals 0, minus 2, minus 4 is minus 6, and again, we have a min. Okay, it's positive definite, it's a min. Is that good? Okay, fine. Okay, fine. We can also write this out if we wanted to. The results we just got this way. And then use Cramer's rule to solve it, right? Put this into there, that into there, that into there, right? Each one of those divided by that, right? hx, hy over h, and h lambda over h. Okay? And we get the 4 and the 6 in there.